Take 3. We're going to keep going ahead with this no matter how awful it is. So Algebra 2, Unit 5, Lesson 4. And underneath my little video there is the title of the lesson, which is Laws of Exponents. So we are going to get into the properties that govern how exponents behave. Now, a lot of these you should be familiar with, but you may or may not be really comfortable with how and why these things work. So we want to get at the nuts and bolts of the different laws and why we do what we do, and also equip you with the knowledge that you need that should you forget the laws of exponents, you can go back and figure them out because you understand how exponents work and where these laws come from. So recall what an exponent is. Okay, so beginning with what is an exponent? An exponent tells us how many times something is used as a factor. Something like that. Let's see if we can do that better. There we go. How many times something is used as a factor. Now, you might have heard it defined as how many times something is multiplied by itself. I used to define it that way, and then I had a student kind of pick apart the phrasing on that, and I'll show you what they meant. So, for example, we have 2 to the 4th power, and that is our way of writing 2 times 2 times 2 times 2. Now, the objection that the student gave you was to the definition, how many times something is multiplied by itself. They said, Ms. Taylor, that's only 3 multiplications. So the 2 is really only being multiplied 3 times, not 4. I thought, okay, well, you're not wrong, which just means we need a clearer definition. We need to have a definition that can't be misinterpreted, or actually in that case interpreted correctly, but it's kind of picky. So an exponent tells us how many times it's used as a factor. Now recall what factors are. Factors, this is where that vocab is so helpful, are things that are multiplied. Okay, so how many times something is being multiplied and how many times it's used as a factor. So when we say that 2 to the 4th power, that 4 tells us how many times the 2 is going to appear as a factor. It's going to appear 4 times. Now, there are 6 laws that govern how exponents behave, and we could make an argument that maybe there's only 5 and that some of them can be viewed different ways, but there are basically 6 laws. Now, lazy teaching would just be, here are the laws, memorize them. The problem with that is that the laws don't make any sense. So even if you are really good about memorizing them, you can maybe pass that test, but ultimately you're going to forget them because they don't make sense. It's just multiply them here, subtract them here. So we want those laws to make sense. So in your notes, you're going to write down the law, the example, and then use the extra space to outline some of that reasoning process. And we know how important that reasoning process is. How do you get your head around what's happening mathematically? And because that reasoning process is what's going to ground you, it's what's going to help you remember it long term. So make sure that you are writing some of that down. Now, you need to understand the reasoning because this is what you will use when you forget or need to refresh the laws. Okay, when you're like, I don't know, should I add these or should I multiply them? All right, so we're going to go through, I think I have a slide for each of these. So the first one is x to the a times x to the b. And the question here is what would you do with those exponents? Okay, so what are you going to do with them? Now, the law says this, x to the a times x to the b is x to the a plus b. And we've actually been doing this one out. Okay, so what I'm going to do is do some of this reasoning thought process. So let's say you're taking your EOC, you're taking the SAT, you see a problem that involves this. You're like, man, I see that multiplication. Should I multiply those exponents? What am I supposed to do with those exponents? Okay, so how could you figure it out? So we're going to pick some small numbers. Okay, we want to pick nice small numbers. What about x squared times x to the 4th? And you're like, man, what should that be? Should that be x to the 8th? Should that be x to the 6th? I don't know. What we're about to do is we're about to go back to that definition. That exponent tells you how many times x is used as a factor. So quite literally, x squared means x times x. That is the definition of an exponent. That is what that 2 is telling you. X to the 4th literally means x times x times x times x. Now, what's happening in between the x squared and the x to the 4th? Oh, well, let me grab the little pointer thing. It's multiplication. So what I have here is just this gigantic string of multiplication. I have x times x times x times x times x times x. This multiplication symbol isn't different from these. Multiplication is multiplication is multiplication. So if you have x times x times x times x times x times x, there's a shorter way to write that. That is x to the 6th. Okay, so for your example, you might write something like this. X squared times x to the 4th is x to the 2 plus 4, which is x to the 6th. And most of the time, we're going to skip that middle piece there, okay, because everybody, I hope, can add 2 plus 4, okay, and get the 6. So in your notes, this statement up here is the law. Like, that's the general statement of this is how the exponents behave. This is an example. X squared times x to the 4th, you would do 2 plus 4 and get x to the 6th. And this over here is the reasoning. This is the breakdown of why you end up adding those exponents. So when I taught Algebra 1, what I would do when we were introducing lots of exponents is that I would give my students a bunch of these to do. And after you're on about the 3rd or 4th one, you start to see, wait a minute, I could do this faster if I just added them. So in your head, you actually start to see all those x's expanded out. And you're like, I don't need to do this. I can just do 1, 2, 3, 4, 5, 6. Okay, so there's the first law. What about this one? This one is x to the a raised to the b. So now you have something, this is called the base. You raise it to some kind of power, some kind of exponent, and then you take that whole thing, make sure you're paying attention to the parentheses there, and you raise that to some other power. So what does that end up being? This is when you multiply your exponents. Now, in isolation, though, you're probably going to forget this. So we can put it on some kind of nice chart and everything, but if you don't understand why sometimes you add them and sometimes you multiply them, or have a fallback way of figuring it out, okay, it's not going to do you much good. So we're going to pick like those nice small numbers again. Now, you can do this with big numbers if you want, but just be aware you need a lot of space in your notebook. So suppose I have x to the 3rd all squared. Okay, so we have to think about what exponents mean. So when we take something and we square it, so notice I'm starting with that outside exponent there. So I'm going to take something and I square it. Well, what does it mean to square something? Well, that means you use it as a factor twice, okay? Or you multiply it by itself. So that's a way of writing x to the 3rd times x to the 3rd, because that's what it means to square something, is you multiply it by itself. Now, here, you might recognize, wait a minute, this is the same thing as what we just did. If I'm multiplying the same base there with the x's, I can just do 3 plus 3. Now, if you're not sure, you can expand it. Years ago when I taught this, I would just say it in class all the time, when in doubt, expand it out. So if you're not sure what you're supposed to do, just dump it all out, okay, because it should still work. So x to the 3rd means x times x times x. And then we have another x to the 3rd, x times x times x. And what's happening in between them? Oh, they were being multiplied, which means that we have another multiplication. So what do I end up having here? X times x times x times x times x times x. Well, that is x used as a factor 6 times. That is x to the 6th. So as an example, you might do something like this. X to the 3rd all squared means x to the 3 times 2, and 3 times 2 is 6. Again, most of the time, we are going to skip this middle step right here because we just do 3 times 2. All right, so those are our first two. And again, here's the law, here's the example, and here's the reasoning. And that reasoning is what you might have to fall back on. So we don't want to jip the reasoning there. It's what we might need to go back to. Next one. All right, now, full disclosure, I actually don't use this law a whole lot. We're going to use it today to prove some stuff and to kind of reason some stuff out. But I actually personally don't like using this one. And so when it comes to the kinds of simplification problems we do with this content, you'll notice like my personal style of doing these problems is I will avoid using this law. I will just find other ways to do it. Which I will demonstrate in a bit. But so here's the law. If you have like bases, and when I say like bases, what I'm referring to is the fact that it's an x and then another x. So I don't have an x to the a and a y to the b, because that's going to change everything, okay? That this is equal to a minus b. And it's always the exponent in the numerator subtracting the exponent in the denominator. So let's reason this out a little bit. Suppose I had x to the 5th divided by x to the 3rd. I'm going to think about this. Like I said, I coined this like little like, when in doubt, expand it out. So if you're not sure, what am I supposed to do with that? The 5 and the 3? Do I subtract them? Do I divide them? I don't know what I'm supposed to do. So we're going to expand it out. So x to the 5th literally means x times x times x times x. You get the idea. And x to the 3rd means x times x times x. Now, before I just start like canceling stuff out. Now, some of you are going to think, okay, well, you can cancel it out. But just to be clear about why we can cancel stuff out, anything divided by itself is equal to 1, including things that I don't know what they are. So like 2 over 2 is 1, negative 1.5 over negative 1.5 is 1, root 3 over root 3 is 1, and x over x is 1, assuming x is not equal to 0. And usually in these problems, that'll be in the direction somewhere. Okay, so that's actually why your x's cancel out. Because if you do x divided by x, that's equal to 1. And what does it mean to multiply something by 1? That doesn't do anything. Leaving me with x times x, better known as x squared. And so you might look at this and say, okay, well, the faster way to get the 2 is to just do 5 minus 3. 5 minus 3 will get you to the 2. So essentially, you're taking all of the numbers in the top and subtracting, like however many you have in the top, you're going to subtract out the ones you have in the bottom, and that's going to leave you with the 2. So as an example, you might write this. X to the 5th divided by, now I got to run out of space over here. I don't really like working it left to right, but that'll be 5 minus 3 or x squared. I fully expect that at times you're going to forget this. So that's why we're going through that reasoning. Like, how did we get here? Because you can always fall back on it. This you might forget. This just means you have to remember what exponents are. Next one, x to the 0. So this is one that is what I would call counterintuitive. And what it means is that it's not what your gut or your intuition tells you that it is. Most of your intuition is going to tell you x to the 0 is 0, and it's not. And it also starts to kind of go against that definition. Like, how can something be used as a factor 0 times? Like, what? Like, then nothing is there. Now, here's what it's, well, I'm going to give you the law last. So what I'm going to do for this one is I'm going to start with the same problem twice. I'm going to use stuff we already know, and then we're going to conclude that both problems are equal. Let's go check it out. So just for kicks, we're going to do like x to the third over x to the third. And I'm going to actually do that twice. So x to the third, x to the third. Now, we know, because of math, we know that anything divided by itself is 1. That is how division works. That's the definition of division. If you want to, you can expand this out. And what you end up with is 1 times 1 times 1, which is 1. So x to the third divided by x to the third is 1. Now, think back to the law we just showed. If you have the same number as your base and you have division, you can subtract your exponents. You can kind of look right back to the example you just wrote down. So this would be x to the 3 minus 3. But what is 3 minus 3? It is 0. Now here's the reasoning involved in this. If we started with the same problem and we did stuff that we know is true and know is okay to do, this is stuff that we've already established in math. Anything divided by itself is 1. We've already established that when you're dividing here, you can subtract the exponents, and we already know that 3 minus 3 is 0. So if we're confident that this line and this line do not have any mistakes in them, then what must be true is that these must be equal. They must be, because we did not make any mistakes. So your law there is x to the 0 equals 1. Now, as an example, you might want to grab your calculator and just try this out with the number. Try 4 to the 0. And your calculator should confirm this. If you put into your calculator 4 to the 0 power, it'll tell you 4 to the 0 power is equal to 1, which usually stymies students a little bit because it's just not what you think it should be. And yet, when we look at the reasoning, when we look at where that exponent of 0 comes from, and it's got to come from something like this, then yeah, like it connects. It's just not what you expect it to be. Okay, so there's that one. Next one. The exponent is negative. Crud. That's no good. So this one is another one where the definition of an exponent starts to break down a little bit. Like, how can something be used as a factor a negative number of times? Well, like the negative is going to come out of some other operations. So with this one, I'm going to do the same thing where I'm going to work the example, like that reasoning out. Okay, and then we'll draw the connection, the rule at the end. So I'm going to do something similar to what I did before. We're going to do like a division problem, and we're going to do the same thing where we set up the same problem twice. Okay, and so this is x squared over x to the 5th. So on the numerator, this is x times x. Now I'm going to do something here that you probably would not think to do on your own, but it'll make sense why I'm doing it. So hopefully we can all agree that I could do times 1. I could do x times 1. That multiplying it by 1 isn't going to change anything about that. Sure, Miss Taylor, if you want to do x times 1, go for it. I don't know why you're doing it, but go for it. In my denominator, I'm going to have x times x times x times x times x. And now I'm going to employ the fact that anything divided by itself is equal to 1. And I end up with a bunch of things canceling out. So I have, okay? Now, the reason I put the 1 there is because my next question is going to be, what am I left with in the numerator? If I don't have the 1 there, I will get the answer nothing or 0. But it's not nothing and it's not 0. What I'm left with in the numerator when I cancel everything out is a 1. So it really, really helps to be able to see that there. And guys, so I'm left with a 1, and then x times x times x is x to the 3rd. And the way I usually reason this out is when I'm doing problems, because I don't like to subtract exponents, is I'll say I have 2x's in the numerator, 5x's on the denominator. I'm going to cancel some of them out. How many am I left with? Well, I'm left with 3. And where are the extras? Well, the extras are in the denominator because there were more of them in the denominator. Now, for the bottom row, what we're going to do is we're going to use that law that says that I can subtract the exponents. So you take the numerator exponent and subtract the denominator exponent. So in this case, it's going to be 2 minus 5. 2 minus 5 is -3. So here's the reasoning again. I started at the same spot with x squared over x to the 5th. Both of these rows do steps that we know are okay to do. Like we know we can expand them out. We know we can cancel things out. We know we're allowed to subtract exponents. In this case, 2 minus 5 gives us a -3. So what must be true is that these are the same. X to the -3 must be equal to 1 over x to the +3. So for my law, x to the -a is equal to 1 over x to the +a. As an example, you might say x to the -5 is equal to 1 over x to the 5th. So a negative exponent becomes a positive exponent when you write it in the denominator. Easy to forget though, so we do want to make sure we're going through the reasoning, like the whys. Why are we arriving at here? Because it's not just some like random arbitrary rule. All right, so that brings us to our last one. So what happens if the negative exponent is already in the denominator? So we just established that if you have a negative exponent, it would be like a positive exponent except in the denominator. What if the negative exponent is in the denominator? So for the reasoning on this, you're just going to have to bear with me, okay? So we're going to do some scratch work here. So 1 over x, we'll just do -2, okay? Maybe if I can write that remotely neatly. That would be 1 over. Now, we just established that x to like the -2 was equal to 1 over x to the +2. Now that lovely gem is something called the compound or complex fraction. And what it is when you have a fraction and then either the numerator or denominator or both are fractions. Now they look hideous. They absolutely look hideous, but they're actually not bad to deal with at all. Once you can like rewrite them to get rid of all the like fraction insanity. So this goes to something, one of my classes today, we kind of talked about this for a little bit, but what is division? Well, division is just multiplication by the reciprocal. So for example, if you have 4 divided by 2, that is the same as 4 times, and what I'm going to do is flip the 2 over. Okay, that's an example with just like numbers. So anytime you have division, you could take that division and make it multiplication, and you just flip it over. That's literally what division is. Only nobody's going to do that to a 3rd grader because that's mean to do to a 3rd grader, okay? Now, what I'm about to do here is I'm going to take that expression in the green. I'm going to do a couple of rewriting steps. So the fraction bar means division. So I'm going to take this fraction bar right here and rewrite it using a traditional division symbol. So this is 1 divided by 1 over x squared. Literally, I just switched notation. So 1 divided by 1 over x squared. Now, if you're like, wait, I didn't follow that, Miss Taylor, this is what I did. If you have 5 divided by 2 or 5 halves, that could be written as this way. Okay? That's all I did. Now, what that does is it first of all, it gets rid of the bigger of the two fractions so that I'm not dealing with the fraction inside a fraction. I just change the symbol over. But it also allows me to take a reciprocal here. So 1 divided by 1 over x squared, remember that anytime you're dividing something, you can rewrite that as multiplication. And so this would be 1 times, and then I'll do the reciprocal. Okay, so now this is gonna come out really nice. 1 times x squared is just x squared, and x squared divided by 1 is x squared. You could also think of it this way. 1 divided by 1 cancels out. Okay, however you want to kind of conceptualize that, that is just equal to x squared. So look at the beginning and the end of this. I started with 1 over x to the negative 2, and I ended with just x squared. So what does that mean? Our law is 1 over x to the negative a is just an absolutely hideous way of writing x to the a. And what we want to get out of this is that negative exponents. Okay, I just can't. Negative exponents are reciprocals. In other words, they just reciprocals. They just flip over. So a negative exponent in a denominator, if you move that factor up to the numerator, it will become a positive exponent and vice versa. All right, now for this one, if you're wondering, this is the law. This is the reasoning, and this you can use as an example. This down here in the blue is like explanation, scratch work for some of the steps that are going on in there. All right, now I actually love these kinds of problems. I just think they're so much fun to do. They're like puzzles. They really are like this, like little puzzles and mazes. And there's more than one right way to do them. In fact, there's a lot of different right ways to do them. And as you practice, you will develop what I call your own style of doing these problems. So on this first one, I'm going to work them out like with just 2 ways of doing it. Okay. Yeah, I guess I'm going to work it out with 2. I'm just like, why did I do that? 2 ways of doing this. Okay. Just so you can see that there's variety. Now, for some problems, like on your homework, you might be able to do them without showing any work. But a lot of these problems, you do need to show some middle steps. So just because you show me a pile of answers doesn't necessarily mean anything. If you're not sure, like, do I need to show work for this problem? I'd be more than happy to answer that for you. All right, so let's take a look at this one. So this first method, what I'm going to do is just remind you that the exponents on the 2 and the x are 1. So that's 2 to the first power times x to the first power times y to the second power. And where this might get a little bit messy, so just we have a lot going on. And where these problems get difficult is when you have multiple laws, like all kind of coming in at once. Okay, I have a timer that's going off in 21 minutes. All right, so this is using that second law that if you have something to a power raised to another power, you would multiply the exponents. What you don't want to forget is that all of this is being raised to the power of 4, not just the y, and that these guys do have exponents there. We just don't write them all the time. So for that first one, it's going to be 2 and then 1 times 4, x to the 1 times 4, and y to the 2 times 4. And I'm sorry, those look a little bit like decimal points, but they're not. So this would be 2 to the 4th, because 1 times 4 is 4. X to the 4th, y to the 8th. Now, a perennial question with these is, can you leave it as 2 to the 4th, or do you have to go find what that number is? I would say, in general, if that number is less than 1,000, you should probably find that number. Okay, so as long as you're in 3 digits or less, you should probably find it. If it's bigger than that, I mean, there's a reason we have exponents in the first place. But 2 to the 4th power is just 16, so yeah, you should probably write it out. How else could you do this? Well, let's say you're just not sure about those exponents of 1. You're staring at the problem like, I'm stuck, I don't know. One of the things you can do is remember what exponents are. So remember I said earlier, when in doubt, expand it out. Like if you're not sure, just take a couple of additional steps. To raise something to the 4th power means you're going to multiply it in 4 times. So what am I multiplying in 4 times? 2xy squared. So quite literally, this means 2xy squared times 2xy squared times 2xy squared times 2xy squared. And this is all multiplication. It is 2 times x times y squared times 2 times x times y. This is like a big old string of multiplication all the way across. You can multiply in any order you want. And we could do a lot of juggling around with commutative properties to reorder that. But essentially what we would end up doing is reordering it. So we would have 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. X. X times x times x times x. Now here we have to engage a different law. Y squared times y squared times y squared times y squared. Well, that's 2 y's, and then 2 more y's, and then 2 more y's, and then 2 more y's. How many y's am I going to have there? Y to the 8th. Now, same problem. We better be getting the same answer. Just using different rules, using different pieces of your knowledge of exponents. One way is not better than another way. So the way that's best is the way that you understand and you can get to that answer and you could explain to me what you did. That's the way that's best. Let's take a look at the next one. Oh, this is so good. And again, there's more than one way that you can do this. There's absolutely more than one way that you can do this. So I might do this one with multiple ways. I might not do it in class just because, we got to watch the bell in class. But in the video, it is 4:18 on Thursday afternoon. I'm still at work. We're gonna have fun with this. So here's what I would do. And this is really the best that I can say. This is what I would do, not necessarily what you should do. Now you need to get to the same place I get to, but which laws you use doesn't have to be the same. So the first thing I see when I'm looking at this is I see y to a power raised to a power. And I know that I can multiply those. So the first thing I would do is -3 times 4 and get -12. And that's going to be over y to the -5th. So we're going to have y to the -12 over y to the -5th. Now, if you remember, I said a few minutes ago, I don't like subtracting the exponents. I just don't like it. It doesn't fit my style for the way that I like to do these problems. But you can. So I'm actually going to come over here and we'll work it out a slightly different way over here for those of you that want to subtract, okay? Here's what I notice. If I have a negative exponent in the numerator, I can take that negative exponent in the numerator and I can write it in the denominator as a positive exponent, because that's what a negative exponent means. And if I have a negative exponent in the denominator, I can move that to the numerator and rewrite it as a positive exponent. It's still not done though. Okay, now this is where I'm trying to think like how I want to do this. we're going to cancel some stuff out. Okay, I'm going to do like another little blurb. I'm sorry that this is getting kind of, okay, but I'm going to do it in my head because I don't want to write out 12 y's. That's just getting too big. I'm going to cancel some stuff out. I have 5 y's in the numerator. I have 12 y's in the denominator. Now, I just went like dot, 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 dot there because I don't want to take the time or the space to write out 12 y's. Now, a bunch of them are going to cancel out. 5 of them actually are going to cancel out. I'm going to cancel them out. So here are the questions I would ask. How many y's do I have left over after I cancel them out? Let you think about it. 7. I have 7 y's left over. Where are the 7 y's? Well, they have to be in the denominator because that's where I had more of them. So the way I would reason this out is I would say, okay, I've got 5 y's on top, 12 y's on the bottom. I'm going to cancel a bunch of them out. I'm going to have 7 left over, and the 7 extras are going to be in the denominator. You are welcome to expand them out, but there's also other ways you can do this problem. So let's kind of look at those other ways. So some of you are going to get to this spot, and you're going to say, all right, I want to subtract the exponents, which you can do. So this will be -12 minus -5. I don't like subtracting a negative, but this ends up being -12. To subtract a negative means to add. So it's really -12 plus y. -12 plus y is -7. And if you have an exponent of -7, that can be written as a positive exponent in the denominator. Okay, take a moment and look at that. There isn't one right way to do this. There is not one right way to manage these problems. Now, there are things that you can do wrong. So I don't want to be heard as you can't get them wrong. Like, yeah, you can do some stuff that's wrong. But what's important is that you're doing enough of these to kind of find the path through the problem that you like. And it does not have to be the same as the path I like through the problem. Okay? All right. Last of these. So for this one, I want to show you just a way of breaking down the problem that I hope would be beneficial to you. What I'm going to do in this first step here is I'm going to split up that problem into 3 little problems. And you'll notice, like, I didn't do any algebra there at all. All I did was I visually kind of spaced the problem out so that, yeah, I just kind of spaced the problem out so that you can kind of visually chunk it. So first part of it is 4 divided by 2, which is 2. Okay. For the second part, you can do this with subtraction. Okay. If you want, and here's the third part. So we got 5 y's, then here we have 7 y's, 4, 5, 6, 7. Okay. Here we're going to cancel one of those out. I'm going to cancel a bunch of these out. And what am I left over with? Well, I've got a 2. I have an x squared that's on the top, and I have a y squared that's on the bottom. That is not the only way to do that problem. So you absolutely 100% could do 3 minus 1 and get the x squared. The x squared there. You can do 5 minus 7 and you would get a -2, and then the -2 would come into the denominator. Okay, that is totally fine, but this video is getting long and we have a whole bunch of practice problems. Okay, so the point I want to drive home is just push forward through the problem and see what you can do with it. And multiple choice, little tip, when it's a multiple choice problem, if you're like very confident about the x's but not confident about the y's, use the x's to eliminate some answer choices. So if you have an x squared and it's in the denominator, that's not the right spot for it. And you can use that to maybe eliminate an answer choice or two. So you don't even have to get the whole problem in order to make forward progress. So that brings us to the practice problems, okay? And there are 6 of them here. I want you to pause the video. Now, this is about a 40-minute long video as is, so it is running long. And that doesn't include the practice review. So pause the video. I am going to go through those problems for those of you that are not in class to go over them, but make sure you are working them. It is going to make the video it's like a bonus video. It's extra. And probably my timer is going to go off because we're down to 9.5 minutes. All right, pause the video. Okay, so I will go through these fairly quickly, and I'm going to go through them fairly quickly on the assumption that you did pause the video and you did take the time to work them out, and you're not going to frantically be trying to keep up with everything that I'm saying because you've already given your brain some time to process it. So for this first one, a to the -2, b to the third. Now the goal here is to make sure that we write that with no negative exponents. Now the -2 only goes with the a, it doesn't go with the b. So when we go to deal with that negative exponent, we're only going to deal with the a. So the b to the third stays in the numerator and the a moves to the denominator. And when I move it to the denominator, the -2 would become an exponent of +2. So the answer to the first one is b to the third over x to the squared, x squared. Okay, and this is one that does not have any work to show for it. Okay, so if you're like, well, I didn't show any work for it, that's okay. Second one, we have xy over z all to the third. So there's different ways you can do this. I'm going to just do it this way because I think this is the way that's going to help most of the people. To raise something to the third power means you multiply it in 3 times. In my numerator, I now have x times x times x, which is going to give me x to the third. In my denominator, I have y, or numerator also, I have y times y times y, and in my denominator, I will have z times z times d. So this would end up being x to the third, y to the third, and then in the denominator, z to the third. You can get there in one step if you use the multiplication and recognize that you would just do 1 times 3 on all of them. Next one. We have 6x squared y over 12x y to the fourth. And again, I'm going to do this one by just splitting it up into like little mini problems. And to save some time, I'm just going to go ahead and make that x squared x times x, and then we have y to the fourth. All right, 6 over 12 simplifies to 1/2. We have some x's canceling, and we have some y's canceling. In my numerator, I have left a lone solitary x. Now, if the x got canceled out as well, you would make sure you need that y. Okay, that's going to be 1x, but since I do have an x there, we're okay. In my denominator, I have a 2, and I have 3 y's. Y times y times y. That is not the only way to do that problem. So if you're looking at your work and you're like, I did some subtraction, I moved this, that, whatever around, that is probably totally fine. You also don't need to show any work for this one. This one is very doable in your head, but you do need to have gotten to x over 2y to the third. So you're like, if it does it matter if the 2 is in the numerator? I would ask you, is there a difference between 2 pizzas and 1/2 of a pizza? Yes. So yes, it does matter where your 2 is. Okay. All right. Next one. Kind of get rid of those first 2 problems. You can rewind the video if you needed that. We have for number 4, 2x, number 4, 2x all to the third, y to the -2. So do note that that -2 only goes with the y. It does not go with the 2 or the x. Now, the exponent of 3 goes with both the 2 and the x because they are in parentheses, and it is the parentheses that are being cubed. So this is 2x times 2x times 2x. And that y to the negative 2, I can take that y to the negative 2, I can move the y down to the denominator, and that's going to make my exponent positive. In my numerator, I have 2 times 2 times 2, which is 8, and x times x times x, which is x to the third over y squared. Not the only way you can do it, but you do need to end up there. So it does need to end up with x to the 8x to the third over y squared. Number 5, we have 2x to the third y to the negative 2. And this one's actually easier. So in this one, the exponent of 3, only goes with the x. It doesn't go with the 2. So if you want that exponent of 3 to go with the 2, you've got to put it in parentheses and then put the 3 outside to make sure you're grouping those together before you raise them. Otherwise, it's just a 2 and then the x to the third. So in this one, the only thing that you can do is take that y to the negative 2 and move it to the denominator and make it y squared. There's like literally no work you could show for that. Now, question 6 is asking you to explain the difference, and I think I'm okay with you guys writing whatever you want if you want me to check it over and make sure that you've answered that. But the idea there is I'm trying to, like, that's where those two problems are coming at, is just to get you to look a little bit closer at the notation and the position of the parentheses. This one means 2x times 2x times 2x. This one just means 2 times x times x, x times x times x. So the parentheses affect what is being cubed. So however you want to explain that, knock yourselves out, okay? And I think we have managed to beat the alarm on my phone, so yay. And you should be good to go on your homework. I know your homework looks like a huge assignment, and that's not my MO, is like I don't give huge assignments. However, it is a lot of them are super, super fast. Like they're going to be really fast problems, like one-step problems. So, all right. And if you've got questions about like which ones do you need to show work on, and which ones are okay to say I did this one in my head, just ask me. Okay, I will let you know, and I'll let you know in the test as well. All right. So hopefully this was like a fun lesson, like little puzzles. Hey, little puzzles. And I will see you in the next one.